Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 5th, 2026, about 3 days ago. It identifies a phenomenon called confident conflicts, where a model is forced to learn data that contradicts its strong internal beliefs as the main cause of catastrophic forgetting, and proposes a new training method that effectively solves this issue. The paper is titled, Entropy Adaptive Fine-Tuning, Resolving Confident Conflicts to Mitigate Forgetting. And as we'll see later, the results are quite striking, showing that we can adapt models to new tasks without degrading their general intelligence. And for those interested in the implementation, the authors have shared their code on GitHub. To visualize this, Figure 1 presents the core concept through both an analogy and data. On the left, the cartoon shows a student forced to label a ball as a truncated icosahedron, which ruins his communication during a soccer game later, symbolizing how models lose general knowledge. The scatter plots on the right confirm this mathematically. The red SFT graph exposes a dangerous cluster of tokens with low probability yet low entropy. These are the confident conflicts, where the model fights against the training data, unlike the blue reinforcement learning distribution, which remains naturally aligned. So, Figure 2 tests this mechanism directly. On the left, Panel A shows a pilot experiment where they simply hide those confident conflict tokens during training. Comparing the stable blue line to the dropping red line, we see that masking these tokens alone preserves general knowledge. Then, Panel B compares the full entropy adaptive fine-tuning method against supervised fine-tuning across 3 domains. The upper bars confirm that both approaches improve target performance equally. However, the lower bars show the real gain. The blue bars for the adaptive method demonstrate dramatically less forgetting than the deep drops seen with the standard approach. Alright. Table 1 details the full performance metrics across different model scales, specifically targeting math tasks while monitoring general knowledge. On the left side, under the math domain, we see that the proposed method, EAFT, consistently matches standard SFT. For instance, with the QN34 billion model, both methods reach a math average around 69%. However, the critical difference appears on the right under general domain. While standard SFT causes a sharp drop, losing nearly 5 points on average as shown by the red numbers, EAFT limits this degradation to just 1 point. This trend holds for the larger 32 billion parameter model as well, proving that we don't have to sacrifice general intelligence to learn new skills. Well, having established the results, Figure 3 visualizes the gradient landscape to explain why they happen. The color intensity represents how strongly the model is being updated, with dark purple indicating intense changes. On the left, the standard SFT graph shows a heavy concentration of dark purple in the bottom left corner, which corresponds to those dangerous confident conflicts. This confirms the model is being forced to relearn against its will. But on the right, under EAFT, that same corner turns light yellow. This proves the method effectively suppresses gradients for these conflicts, shielding the model's original beliefs from destructive updates. So, to ensure this method is practical, Figure 6 analyzes the trade-off between approximation accuracy and memory cost. Instead of calculating entropy over the entire vocabulary, the authors use a top K approximation. The red solid line shows that accuracy rises sharply, reaching a correlation of 0.999 at just 20 tokens. Meanwhile, the blue dashed line indicates that memory cost stays nearly 0 in this range. The green shaded region marks this optimal spot at K equals 20, proving the approach adds virtually no overhead. Alright. While Figure 6 just showed the efficiency, Figure 5 pulls the performance metrics together into a trade-off analysis. The vertical axis tracks the new math task, while the horizontal axis measures general knowledge. Look at the red dot for standard SFT in the top left. It learns math well but suffers severe forgetting. By comparison, the green dot for masked SFT moves right to save general knowledge, but it drops on the vertical axis because it fails to master the target task. Finally, the cluster of EAFT variants in the top right achieves the ideal balance, maintaining high scores on both dimensions. Wrapping up, the evidence suggests that catastrophic forgetting stems from forcing models to accept confident conflicts. By simply using entropy to filter these updates, EAFT enables efficient specialization without erasing general intelligence. This offers a robust, low-cost alternative to reinforcement learning for domain adaptation. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.